kid growing up in a rural village in Bengal, in the immediate aftermath of Indian independence, the kid had ambition, modest, like his fellow classmates, to become a school teacher. But once he joined his MSc class in Bardwan University, the inspiring teachers motivated him and he set his goal higher. Today, he is a J.C. Bose National Fellow of Department of Science and Technology, Government of India. He is elected member of number of academies, including Indian National Science Academy, Academy of Sciences, Indian Academy of Sciences, and the Third World Academy of Sciences. He is a world-known researcher in the area of nuclear physics and neutrino observatories. That is Professor Naba Mondal. Welcome, sir.
Thank you.
We would like to first know about your childhood. Where were you growing up? What happened in your childhood? How did you get interested in science?
Well, I grew up in rural Bengal, and as you can imagine, like any other rural places, my exposure to science was not that much because I grew up in a local or village area. But when I used to like physics, I used to like this, but that was a subject, just it, not beyond that. However, when I came for my MSc in the University of Bardwan, then actually I was lucky to have few of my good teachers who inspired me. And actually through one of them, I came to know about TIFR.
Okay, who is that?
Actually, this is actually Professor Siranjan Banerjee. Okay. He was an astrophysicist, and he told me, why don't you, think of TIFR, go there.
I also think that your father had a very important role in, forming your character.
Yes, my father actually, I was tremendously influenced by my father. Actually, my father, he lived in his entire life in our ancestral village. Okay. And he did go to school, but he couldn't complete his matriculation because of the untimely death of my grandfather, and he had to take care of the family. But from his limited exposure and in the school, he knew the value and importance of education.
He was himself a school teacher?
Yes. No, he was not a school teacher. Okay. He actually was a farmer. Okay. But he knew because the importance of education. So he actually never even asked us to do anything else other than study. And that actually helped us a lot. And and otherwise, from the village to come up is not so easy. You have other things to do. Yeah.
So once you joined Bardwan University, what kind of changes took place in you?
So actually, I used to study physics. I used to like it, and it was one of my favorite subjects. But it's like that. But I started enjoying physics after I came to university because of the way I was introduced to the subject. And I started thinking differently about science, think about it and think about, how things work. So that actually changed a lot because there was some good teacher there. Yeah. And as I told you that through them, I came to know about TIFR, and then here I am.
So when you joined TIFR in the initial years, what is the kind of thing that you worked on? What was your experience in TIFR coming from a Bengal rural area to a cosmopolitan city like Bombay?
In fact, I'll tell you a story. In fact, I came here before I joined TIFR. I came here as a student to visit TIFR. Oh. And I just, as an educational tour. And then I came here and I saw the place and I was just moved actually. And I just, asked even, before that my teacher have already told me about TIFR. I just thought that, okay, it will be very nice if I can come and work here for my PhD days. And fantastic. And that was the ambience and atmosphere of TIFR. Even when I came that time, there were large experimental groups, large theoretical works was going on, and there was, TIFR was always
a, international repute.
Even if you sit down in the canteen, you will be discussing a lot of physics and all the time, and there are all the time lectures going on, colloquium going on, and so it was a really wonderful time. And you get
atmosphere of education, atmosphere of knowledge.
Absolutely. Yeah. So that was the situation
there. That's really interesting, and it's very fortunate that people like you have been able to get this opportunity to.
Absolutely.
You have been here for a number of years in TIFR.
37 years.
37 years. It's a very long time in a research field. If you look back, and then you want to look at, let's say, 3 of my best works, okay? I mean, you would have done number of projects, number of research, number of papers, of course, obviously in this 37 years. But if you want to put 3 as a highlight, what will you do with?
Well, no doubt, I will put at the top is my PhD work at Kolar Gold Field.
Okay.
Originally there, I was to work on a different experiment for my thesis.
Okay.
But this was 78, and that time the whole world, the particle physics community was excited about the the prospects of the grand unification,
Okay.
that theory proposed by Abdul Salam and Yogesh Poti, an Indian scientist, and also simultaneously by Stephen Weinberg and Sally Glasso. And they had this idea that all the three forces, that is strong, weak, electromagnetic, will be unified, and as a result proton will decay.
Okay.
And there was a plan to start a lot of proton decay experiments in United States, in Europe. So we also decided to have experiment of our own.
Okay.
And we set up that experiment. And I would say, and we are the first actually to start the dedicated proton decay experiment anywhere in the world.
In the world, okay.
And why I put it at the top ranking experiment? Because in my actually entire career, because
It's like your first love.
first love, not only that, see, when I came there, I was just a raw graduate student. But I had this wonderful opportunity to work on this experiment from
The scratch.
build up the experiment.
What will you put as a second?
So this is okay. This is my KGF experiment, and then my second I will put my participation in the international collaboration experiment called DZero at Fermilab in the United States.
DZero in Fermilab.
DZero in Fermilab. This is a much sophisticated instruments, of course, compared to my PhD thesis work. This is actually the detector was built to look for the proton antiproton collisions, and look for that time top quark was not discovered.
Okay.
Higgs boson was not discovered. The supersymmetric particles are not seen.
You are talking about 1980s, mid 80s.
Mid 80s actually. So when I came there, and then so that was my, and of course we had this. I had this opportunity to work some of the best minds of the world in that experiment, because it is a large collaboration. And of course, 1995 we discovered the top quark in that experiment.
In that experiment, and you are also part of
that.
That's really great. So what would you put as a third one?
The third one I will put, of course, my current plan is that I am doing is the India-based Neutrino Observatory, because it is to go. It is a big dream actually, but we have not gone anywhere yet.
Yeah.
We are just have some prototype built, some ideas, some physics studies is going on. So of course, when it will come, it will be much bigger.
Much
and
bigger.
I hope the future generation will be using this detector to get the physics out of it.
See, you said that sometime in your career, you worked in US in the Fermilab, which is a very different research atmosphere,
That's
right?
That's right.
So how do you look back at it? I mean, looking back at it, I mean, what do you feel? I mean, like, what should we do in India? What was your experience in Fermilab?
I'll tell you this one. So before that, I have already participated in my PhD experiment at Kolar Gold Field. I have participated in all aspects of doing an experiment, from building particle detectors to putting the electronics and putting it together and looking into data. So I went to DZero experiment. This was a much sophisticated, but basically the same thing we are doing. So I have not learned any new way of doing.
So which means that even under trying conditions, Indian conditions were making
So,
world-class people,
and on
right?
top of that, I also, along with me, there are many other Indian students or Indian physicists working in the DZero experiment from different universities, from US universities, and they are playing key role in that experiment also. So then I realized that, look, I mean, all these Indian students and Indian physicists are doing excellent work here. So definitely, given an opportunity, given a facility, they will be able to do similar excellent work in India also, and we need that.
We'll continue discussing. Before that, we'll take a short break and then let's come to the discussion once again. Welcome back to this show. Imagine that you go deep inside the earth, about 2 kilometers. Obviously, it will be pitch dark. It will be humid. It will be sultry. Perhaps only your assistant will be there, no other soul. You are all alone. That is the condition in which Dr. Naba Mondal, today's our guest, started his career in science. Let's ask him about his experience in Kolar Gold Fields. What were you doing there?
Well, I was there to do originally my thesis work, and that time there was the experiment that was supposed to do is to study multiple muons. Those are the penetrating muon, very energetic muon produced by the cosmic rays and gone deep underground.
So basically, it's like a cosmic ray coming
Created,
from space.
and then they go through the earth rock, and then we'll detect them. By studying them, we'll be able to understand the composition of the cosmic rays. So that was the idea. I set up that experiment. It needed something like 300 proportional counters. This is the particle detectors. We built them quickly within something like a year or so, built all the electronics and ready. And it was running. I was very comfortable that now my thesis experiment is running. Right. I have to just get the data and analyze it and get the thesis out of it. Well, that's not supposed to be what is going to happen.
What we planned doesn't happen exactly.
It didn't happen. What happened is that this is the time when whole particle physics community was excited about this, the grand unification and the corresponding consequence proton decay.
Okay.
And there was plan to set up experiment. So our group also decided to do that experiment there. But and we are all excited. But what is meant to me is that I have to stop that experiment. Instead of 300, I have to now build 3,000, 10 times more proportional.
300 to 3,000.
And then all those things we have to build and then make it actually again work. So this was really a challenging job, but we decided to bite the bullet. And then, so now we set up almost a cottage industry at Kolar Gold Field to make these proportional counters.
So in the KGF you are doing from 300 to 3,000? 3,000
proportional counters so you have to build for this proton decay experiment. And but how to make that? But then you have to be competitive because you cannot wait too long, and we didn't have too many people there. So we started almost a cottage industry for making those proportional counters 24 hours a day. We are making that one. But the problem is that we didn't have too many people working at Kolar Gold Field that time. It was myself and one of my Japanese colleagues who was there, and then we have some scientific assistant. Of course, my group members used to come. So that was not enough actually. So we decided how to solve this problem. So what I did, I went to the local KGF college and gave some lectures to the students and how exciting they are. Some of them got excited. They came actually and helped us. And
so basically you mobilized a volunteer force to get
your things done actually.
Yeah? Interesting.
And now, and those days, you have to take those proportional counter underground, build your detector slowly and make it so all the counters.
So when you go underground, how much time you will stay there?
Yeah, first of all, even to take those counters underground, you have to use the same sap where the miners use for taking their ore out. So we used to get that sap only in the night. The cage was available to us in the night. So whole night, we used to take the proportional counter down, and daytime we go there and set it up. And you have to stay almost. We used to spend whole day. We used to take our lunch in a tiffin carrier, all of us, and spend their time.
So basically you were in a cave for almost, how many years you were there in that KGF experiment?
Okay, we actually, this experiment, the exciting experiment that we are doing for, building that one for 5-6 years, running it, but that experiment continued till 1992.
Yeah, but you were spending there for about 5 years.
Yes,
inside
as a main person, as a student there, working for my experiment there for 5 years.
That's
yeah.
Okay, this KGF experiment, you put these counters.
Yes.
What was your result?
So that's right. So we got some early results, in terms of looks like some proton decay candidates, but later on it can be explained by the background. So it puts a limit on the proton lifetime. So remember that time what the theory of Abdul Salam and Jageshpati was telling us is that proton's lifetime is something like 10 to the power 29 years.
10 to the power
if that was
years.
true, that was true, then we would have we should have
got some
had
evidence.
Large number of events at that particular energy, which we didn't see, only a couple of them. And later on it can be explained by the neutrino background. So we could put a limit on the proton lifetime.
Okay, so that is one kind of result that you got from that experiment. And I believe that that was closed down somewhere around 90s, right?
92.
92 it was closed down. Why was it closed down?
It was closed down. See, we are there courtesy to the Bharat Gold Mines Limited. Who are basically running that for the extraction of gold and for their mining operation. But the gold was not anymore available in the mine. So they were running under loss. Year after year, the gold mines were running under loss. So they decided, though it is a public sector undertaking, but they decided to close it down. And once they closed it down, we didn't have the resources or kind of funding to run the mine, the operation of the mine of ourselves. of course, when we heard that it will be closed down, and we approached the central government, we approached the BGML to give us some estimate what will be the cost, and they gave it a number, and it was a really big number. So we approached the government, but they didn't have that kind of fund for us. So we had.
But looking back now, what do you think? We should have closed down or we should have continued?
I mean, see, if we could not have continued just for the experiment, because see, this, the Kolar Gold mines is a large, big networks of tunnels. So you have to maintain the whole thing, and that's a very. So if you are running the mines, then you can, continue it. But that was not the case. So even if you go there now, it's completely underwater.
Underwater, okay, because the sea underwater is. But I think that experiment is one of the milestones in Indian modern science.
Yes,
right?
absolutely. And if that place, that was the deepest mine anywhere in the world. Now, after the closure of the KGF, the next deepest mine is the mine in Sudbury in Canada. And that place has become a mecca of many of these experiments, like dark matter search experiment, double beta decay. Some of the modern experiments are being conducted there. So if KGF would have been there, we would have done similar experiment here, even attracted the world community to come here.
We need to continue more. I mean, we need to discuss about your recent passion, Neutrino, which we'll do in the next section. Welcome back to this show. We have Dr. Naba Mondal, Senior Professor from TIFR, spokesperson for the India-based Neutrino Observatory with us. In this section, we'll discuss about neutrinos. Popularly, neutrinos are called as ghost particles. Just like ghosts, they are hard to catch. They are there, maybe ghosts are not there, but neutrinos are there certainly. They are in huge numbers. Just in the thumb area, something like 1 centimeter, cubic centimeter, you have 330 neutrinos. Every second, something like 100 trillion neutrinos pass through us. Okay, it's around us. But it's very hard to catch because it's electrically neutral. So you cannot use magnetism or electricity to detect them. And it is this particle that Dr. Naba Mondal is planning to capture. So can you explain what is neutrinos?
Actually, neutrino is an elementary particle, just like it's similar to an electron, okay? But it doesn't have the charge
what we
like the electron has.
Learn in school like electron, neutron, proton.
Yeah.
Like
there is a fundamental particle, another particle, but only difference that it doesn't have a charge. It's a neutral particle. And this is actually it always associated with the electron. But in fact, as you know, electron also has two cousins, heavier cousins called muon and tauon.
Yeah.
And each of these three particles, electron, muon and tauon, has an associated electron with them. Okay. So for example, electron has the associated electron neutrino, muon has the associated muon neutrino, tau has the associated tau neutrino. Okay. So these are the three neutrinos. And as you have said, there are 300.
It's like vada and pav.
Yeah.
They have to be together.
They have to go together. So, and then there are 300 such neutrinos even created during the Big Bang. Okay. Is there every cubic centimeter of this space that you have mentioned. Yeah. But apart from that, neutrinos are created by many sources. Okay. For example, in the core of the sun and sun-like stars, neutrinos are produced in a large number. Then the neutrinos are produced inside a supernova explosion. When the star dies, that time neutrinos are produced. Neutrinos are produced in all the nuclear reactors that we have. Okay. They're copiously produced in those reactors. They are even produced in the Earth core. There are lots of radioactivity there, and they produce a lot of neutrinos, naturally reduced. You can produce them in accelerator, okay, also, and then study them. So all these different sorts of neutrinos are being used for studying neutrinos. Now the questions come, why neutrinos are so exciting area of research today?
Yeah. That's exactly the question that I want
to. So that is basically because what we used to know about neutrinos is that, well, it's a particle, it doesn't interact much, as you said, it's the ghost particle, it doesn't interact, it interacts very weakly, and that's it, but it has no mass in the standard model. But the recent experiment...
No mass in the... I mean, that's what we thought till now, right?
Yeah, okay. But the recent experiment has shown that the neutrinos changes its type. That means it oscillates from electron neutrino to muon neutrino to tau neutrino, and so on. And this oscillation is possible only if neutrinos have mass, but a tiny mass. So it does have a mass. And that makes neutrinos most exciting area of research today.
So you say that there are three flavors of neutrino. Yes. And they may have mass. And then one of the biggest question today is which one is the heaviest and which one is the lightest among the three. That's a kind of question that you are saying that we are grappling with. And how are we going to detect this in this India-based neutrino observatory?
Yeah. See, in our detector that we are going to put underground, first of all, we have to put it underground because neutrinos hardly interact. If you do it on the surface, all the other cosmic ray particles will be huge background. So if you go underground, all the cosmic rays get absorbed, and then you get only the neutrinos there.
So you are something like a sheave. I mean, you are eliminating all the cosmic rays, and then only allow the neutrinos largely.
to go, largely. And then we have this huge 50 kiloton detector with 30,000 particle detectors called registry plate chambers. And when the neutrino comes,
what is this size you said?
So this is actually 50 kiloton.
50 kiloton.
Yeah, and the size is, it will be 48 meters by 16 meter by 14.5 meter in height.
And then how many detectors you said?
30,000 particle detectors called registry plate chambers. Now,
what is this registry plate chambers?
This is actually two glass plates separated by a small 2 millimeter gap.
2 millimeter gap.
2 millimeter gap. And whenever a charge particle goes through that gap, it will create ionization in the gas, and that will create some electron, and those electrons will be collected and we will get a pulse actually. So collecting those pulses and along the track of the particle, we will be able to find the track of the particle.
So it is something like, for example, if you go to a seashore, if you see the footprint, that you know that somebody has walked.
That's right.
Something of that kind.
And this is how we are going to do that one. And and then what will happen is that so the particles will neutrinos will come, and the neutrino will interact in those iron plates, and then produce a charged particle called muon. Because it's actually the
you are not directly detecting the neutrino, but it's only something that it is creating.
Because neutrino is a chargeless particle.
So it's very difficult. Yeah.
So when it interacts, it will produce a muon. Now, depending upon whether it is a neutrino or an anti-neutrino, it will either produce a mu minus or a mu plus. And then we will be able to, and then we have a magnetic field. In that magnetic field, a mu plus will go in one direction, it will bend in one direction, and a mu minus will bend in the other direction. So their curvature will be in opposite direction. So you know the event is a neutrino event or an anti-neutrino event. And that's important. If you can identify that, that will be useful for this mass hierarchy problem.
See, but this is not the only neutrino observatory. I mean, there are others. I mean, I read that there is something being built in Antarctica called Ice Cube. There are many others. So why us? I mean, why this?
So, yes, you are right that there are quite a few large neutrino experiment is coming up all around the world and even running now. I mean, the Ice Cube in South Pole is running already. But every experiment has a purpose. For example, the Ice Cube that you talked about is to detect neutrinos coming from neutrino sources in the sky. Very ultra high energy neutrinos they will be detect, and from that they will point and find out which direction they are coming from. There are experiments happening in China and Korea using the reactor neutrinos. They want to measure some of those oscillation parameters. The neutrinos are oscillating from one flavor to another. They want to measure some of the parameters.
How does they change from one to another?
The experiment that we are doing is to address the neutrino mass hierarchy.
It's a very specific
question. And our detector, because it is the largest magnetized detector in the world, it has the unique opportunity to address this mass hierarchy issue. That's our importance actually.
It sounds very interesting. I mean, I think we are also doing by this international class physics, not something small one, but addressing a big question. I mean, a nation like us should certainly enter into this. But then there are some people who are raising certain concerns. I mean, like this building this detector is going to cause environmental problem in that region which has been chosen. What do you?
Well, I mean, you have seen our proposal. What we want to build? Yes, we have to build underground laboratory, and we will make a 2 kilometer long tunnel. That's it. Now you see the tunnel making is a common thing in India today. I mean, if you go to even metropolitan cities for these underground railways and we make tunnels. And 2 kilometers tunnel is not going to change any difference, no environmental damage or any such things.
No substantial issues are going to arise.
No question. And not only that, whole thing will be underground. We will not touch any tree in the forest or anything, because it will be whole thing underground.
So the environment is not going to be anyway changed at all.
No, there should be any.
And also this is only a detector. It's like keeping a thermometer to measure the temperature. You are not going to create any neutrinos. I mean, it's only that neutrinos from others.
Neutrinos from the cosmic rays is creating in the atmosphere, and they will be going. And they are going anyway through us and through everybody, and so they are there. So we are only detecting.
See, one more question that people are asking is that India is still a poor country. I mean, something like about 30-40% of India is still, below poverty line. Should we do this? I mean, should we put money into this? What do you...
So first, I mean, let's not have the debate whether India is a poor country or a rich country, because that is also debatable. But question is, I mean, any country which one aspire to be a developed country must invest in science infrastructure for that one. And I will give you the example. We in India, we put something like 0.88% of our GDP.
So 0.88, less than 1%.
Less than 1% for science and things like that. And South Korea is spending something like 3 to 4% of their GDP for that.
Korea, a small country, is spending about 3 to 4%.
And US is spending something like 7 to 8% of its GDP for science. Now you can see the state of development of each of these countries, and you can
So
imagine
in some sense, the spending towards science and technology and the
is
development
absolutely necessary. If you want to move from a developing to a developed country, spending in science is important.
Particularly when we are talking
And
about
especially
knowledge
the
economy
experimental-
and...
yeah, especially in the experimental areas, because that will spawn also new technology.
technologies.
Yes.
Okay. So you mean to say that by investing this, we are not only doing some research, but we are also,
Yes.
there is a spin-off technologies
I
are
mean,
possible.
take for example, let's take example CERN in near Geneva,
Yeah.
which has invested billions of dollars to make this large hadron collider, okay, to discover Higgs bosons and other particles.
Yeah.
Yes, that's the science goal of that one.
Yeah.
But look at what is the technology spin-off from that laboratory itself.
It's
The
enormous.
WWW has been invented there. All these medical imaging particle detectors are there. The grid computing is major contribution coming from there. It's just if you start counting the benefits of science, is just you cannot imagine.
So I want to ask one question. 37 years you have been in this research field. Before that, you were a kid from a rural area, perhaps having, thought that you will become a teacher. What do you think? Are you satisfied?
Oh, yeah, absolutely. I mean, I have the most exciting time in my during my entire research career. And imagine, you are doing what you are paid for, what you want to do. I mean it's just like that. You want to discover new things and in science, and I'm paid for that one. I'm
Maybe you are not very rich, but then I
I'm
think
grateful to the country for giving me and people like us opportunity to do whatever you want to do in science actually, and make new discoveries.
Thank you, Dr. Naba Mondal. It was very nice talking to you, and I think this will be very inspiring for the young India that's in the offing. And we thank you once again for participating in our program.
Thank you very much.
Thank you.